Today we're going to look at how to find the distance between skew lines. Skew lines, let's see, skew lines here, they're lines that they are not parallel. So v of r, the direction vector of r, is not equal to some lambda times v of p, the direction vector of our p, our line p of s. Okay, and do not intersect. So based on this, we then know that the line r of t, which I have drawn just some generic r of t here, and some line p of s, these lines, they are not parallel, they don't intersect, so they must exist on parallel planes. So exist on parallel planes. All right? Oops. Let me draw an E in there. E-S. There we go. So what does that mean? That means that if we then look at two planes in which r of t and p of s are contained, we know that they each have a normal vector. We can call this np, and we can call this normal vector nr. Okay, these normal vectors are parallel because the planes are parallel. So nr is parallel to np. That means that nr is equal to some lambda np. So what I'm going to do is I'm just going to let them equal each other because I can. So now we need to figure out how to find this n vector because it's going to help us. And we also need to figure out why it's going to help us. So the first thing we do is I've drawn a line which is the distance between the two vectors. I can label this D. This is D right here. It is the distance between two vectors. So if we can drop a perpendicular line from one vector to the next, that will tell us the distance between the two vectors. The next thing we're going to do is we're going to identify 2 points on each line. And what I've done is I've used the 2 points given in the definition of each line. So here's our initial point. We can call this x naught. And here's the other initial point, x naught. So this is x naught for r, and this is x naught for p. And so we have these two are on this line. So we can draw a vector between them. And I've done that. Now, this vector may or may not be perpendicular to both lines, but there's a way to figure that out. What we can do is label stuff, like what is this vector? Now, this vector is equal to the end point subtracted component-wise by the initial point. And doing the math, we get this. So now I've got my A vector. I know what the components are of my A vector. So now we're going to use this vector and the line that we have called the distance, and we're going to figure out how, with these two pieces of information, we're going to find this distance. So we can say the normal vector is parallel to the distance segment. So I'll use this line for a line segment, okay? And they're parallel to each other because to find the distance, we need to drop perpendicular line from one vector to the next vector. It needs to be perpendicular to both. Now, this vector that is parallel to the distance then allows us to do mathematical operations that we have learned. So now we have two vectors. We have the vector A and we have the vector n. The vector n is parallel to the distance, and the vector A may or may not be. In our picture, it does not appear that it is. In order to figure out this distance, we can realize that the distance is equal to the projection of the A vector, projection of the A vector onto, so of A onto the n vector. We don't want the vector, we want the magnitude. We want the length, the distance. So that's why I have the magnitude piece here. The projection is the dot product of the normal vector with the A vector. Now, we can get rid of this unit, this unit vector, because it does not change the length of the projection. So this is just equal to 1. And so the component of the projection that is parallel to the normal vector is n dot A over n, the magnitude of n. Okay, so that's great. Now we know a formula to figure out D. But what is n? So how do we figure out n? N is a vector that is perpendicular to both the line r of t and the line p of s. Both of these lines lie on planes that have normal vectors. Whoops, I jumped ahead. R of t lies on the plane, this top plane, and it has a direction vector, V sub r, because it's on the line r. I named it V sub r. And this is perpendicular to its normal, to this plane's normal vector. And V sub p is also perpendicular to its plane's normal vector. And this normal vector, we said, is then perpendicular to both lines and orthogonal to both planes, which means we can use the cross product, because the cross product produces a vector that is perpendicular to the two vectors that it is crossing. To do that, I'm going to use the determinant method, and we get -1 times 0 minus 1 times -3 in the I direction. And then we've got the j direction here and the k direction. And simplifying that out, we get the vector 3, -4, 4. So now we have a normal vector. And we have a formula to find the distance between the two planes by doing the dot product with the A vector and the normal vector divided by the magnitude of the normal vector. So here you go, the dot product divided by the magnitude. And then that's equal to this quantity, which simplifies down to 11 over the root, over root 41. And so that's the exact answer. So at this point, most people want to box their answer and move on. In math, it is important to communicate what you are mathematically modeling. So I would add a conclusion that says, so given the two skew lines above, the distance between them is 11 over root 41, which is approximately 1.71791 units. So at this point, this is the method that you will use to find the distance between the skew lines. Thank you.